At its heart, chemistry is really all about change. But it's not just about if a change is going to happen, it's also about how fast. That's exactly where chemical kinetics comes in. So in this explainer, we're going to break down all the concepts that control the speed of reactions so you can absolutely nail this topic on your exams.
I mean, just think about it for a second. Some reactions, like the fuel in an engine, are just explosively fast, right? Over in a flash. But then you have other things, like an iron gate, slowly rusting. That takes years. They're both chemical changes, so what's the difference? What's controlling the clock? That is the big question, and we are going to answer it.
Okay, so let's get one thing straight right off the bat. In chemistry, we're always asking two main questions about any reaction. First, there's thermodynamics. That tells us if a reaction is even possible. Is it feasible? But then there's kinetics, and that answers the really practical question. Okay, if it can happen, how fast will it actually go? You've got to understand both to get the full picture.
And here is the absolute best example of that, the diamond paradox. Believe it or not, thermodynamics tells us that a diamond will spontaneously turn into graphite. So why isn't your diamond ring turning into pencil lead? Well, the answer is kinetics. The rate of that reaction is so ridiculously slow, we're talking millions of years, that for all practical purposes, it doesn't happen. It just perfectly shows the difference between what can happen and what actually happens in a normal amount of time.
So, here's our game plan. We'll kick things off by figuring out how to define a reaction rate. Then we'll dive into the most important equation of this whole topic, the rate law. After that, we'll see how to use it with something called integrated rates, peek behind the curtain at the theory of it all, and then we'll wrap up with a quick reference guide that is going to be perfect for your exam revision.
All right, first up, let's get a really clear and precise definition for what we even mean when we say the speed or rate of a reaction.
Officially, the reaction rate is just the change in concentration, and that can be of a reactant or a product over a certain amount of time. I like the car analogy. A car's speed is distance over time, right? Well, chemical speed is just concentration over time. And a pro tip for exams, keep an eye on the units. They're usually moles per liter per second, and that can be a huge clue in a problem.
So let's imagine a super simple reaction where reactant R turns into product P. We can actually measure the speed in two different ways. We could watch how fast the reactant R disappears, or we could watch how fast the product P appears. Either way, we're measuring the rate of the reaction. Makes sense, right? Okay, now we are getting to the absolute heart of chemical kinetics, the rate law. This is the master equation. It's the mathematical rule that tells us exactly how the speed of a reaction depends on how much of the reactants we have.
And here it is in its most common form. The rate law basically says that the rate of the reaction equals some constant, which we call K, times the concentration of each reactant, each raised to some power. Now don't worry, we're going to break down what K, X, and Y all mean.
Let's start with K. That's the rate constant. The best way to think about it is like a reaction's unique speed fingerprint. Every single reaction has its own K value, as long as the temperature stays the same. And here's the key takeaway. The bigger the value of K, the faster the reaction. It's that simple. Now for those exponents, X and Y. These are called the orders of reaction, and they are so important. They tell you exactly how sensitive the rate is to a change in each reactant's concentration. For example, if a reaction is first order for reactant A, that means X equals 1. If you double the amount of A, you double the speed. But if it's second order, where X is 2, doubling A would actually quadruple the rate. The overall order is just adding up those exponents, X plus Y.
Okay, everyone, listen up because this is a classic exam trap. You cannot, I repeat, cannot figure out the orders X and Y just by looking at the numbers in the balanced chemical equation. The rate law must be found by doing an experiment. It's an experimental fact, not something you can just guess. Please burn that into your brain.
This brings us to something that trips up so many students, the difference between order and molecularity. Remember this, order comes from experiments. It describes the overall reaction and tells us how concentration affects the rate. Molecularity, on the other hand, is a theoretical idea. It just describes how many molecules are bumping into each other in a single tiny step of a reaction. Order can be 0 or even a fraction. Molecularity is always a nice, simple whole number. Do not get these two mixed up.
Okay, so we've got the rate law down. Now what? Let's see how we can actually use this to make some real predictions. we're going to learn how to figure out the concentration of a reactant at any point in time, using what we call the integrated rate laws. So, the rate law we've been talking about is technically the differential rate law. It's great for telling you the speed at one specific moment, but what if you want to know, hey, how much stuff is going to be left after 10 minutes? For that, you need the integrated rate law. It's basically a version of the equation that's been rearranged using calculus to give you a direct link between concentration and time. Now, for your exams, you don't need to do the calculus, but you absolutely need to know how to use these final equations. So let's walk through a typical exam problem together. We're looking at the decomposition of N2O5 gas, and we're told it's a first-order reaction. Okay, here's our data. At the start, time equals 0, the pressure is 0.5 atmospheres. After 100 seconds, the total pressure has gone up to 0.512 atmospheres. Step 1. We find the right integrated rate law for a first-order gas reaction. There it is on the screen. Step 2. We just substitute our values in. T is 100, P initial is 0.5, and P at time t is 0.512. Step 3. We plug those numbers into our calculator and solve for K. Feel free to pause here and try the calculation yourself to see if you can get the final value for that rate constant K.
So far, we've covered the what and the how. Now let's explore the why. What is actually happening down at the level of individual molecules that makes a reaction fast or slow? This is where collision theory comes in.
Okay, the first big idea here is activation energy, or EA. For any reaction to happen, molecules have to collide with each other. But here's the catch. Not just any little bump will do. They have to smash into each other with enough energy to overcome a barrier. The best way to picture it is as an energy hill. The activation energy is just the minimum amount of energy needed to get over that hill and turn into products.
And this graph beautifully explains why temperature is such a big deal. This is called a Maxwell-Boltzmann curve, and it shows the spread of energies for molecules in a sample. Now watch what happens when you raise the temperature. The whole curve shifts to the right. Look at the area under the curve that's past that activation energy line. Even a small increase in temperature creates a huge increase in the number of molecules that actually have enough energy to make it over that hill. That's precisely why heating things up makes reactions go so much faster. But wait, there's one more piece to this puzzle. Even if two molecules collide with a ton of energy, they also have to be facing the right way. This is what we call the orientation or steric factor. Think about it. If they hit each other backwards or side on, the right atoms won't be in place to form new bonds. They'll just bounce off each other, no reaction. So for a successful reaction, you need two things: enough energy and the correct orientation.
Okay, let's wrap this up by consolidating everything into a high-yield summary. This is the stuff you absolutely positively need to have locked down for your exams.
This slide right here, this is gold. Go ahead and screenshot this for your notes. It lays out the key differences between zero and first-order reactions. Notice three critical things. 1. The rate law. For zero order, the rate doesn't change, but for first order, it totally depends on concentration. 2. Look at the units of K. I'm telling you, this is a classic giveaway on exams for finding the order. And 3. Memorize those half-life formulas. Notice how they're completely different for each order.
Let's finish up with a quick pop quiz to see what you've learned. First, a conceptual question. Can you name the main factors that affect the rate of a chemical reaction? Give it a thought. If you said concentration, temperature, and catalysts, you are absolutely right. Now for a quick calculation. If the rate constant K for a first-order reaction is 200 per second, what's its half-life? Go ahead and pause to try it. All right, you should have used the formula T half equals 0.693 divided by K. That gives you 0.003465 seconds.
So, I'll leave you with this final thought. This stuff isn't just theory for an exam. Understanding kinetics means you can actually control the world around you. How could you use these ideas to speed up the creation of a medicine? Or maybe slow down the rusting of a bridge or the spoilage of food? The principles we talked about today are absolutely everywhere. Thanks so much for joining this explainer, and good luck with your studies.